think we're probably live. Looks like we are live. Hello everyone. Welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today we will be going over some commonly asked mathematics questions to help you with, and these questions will be at both the high school and college levels. If you need some help with homework or with some tutoring, check out the links in the description below. Awesome, so let's get it started with the questions that we have today. Just gotta switch over to my screen. Nice. So here is the first question that we will be solving today. So the question asks, which graph represents a geometric sequence? So we have four options. This is a little bit of a multiple choice type question. Our first option looks pretty line-like. Okay, straight line. Interesting. The second one, it's a little bit curvy. Interesting. The third one, it's a little bit curvy, but a little bit more sporadic. It seems to be curving down. And this one, I think that follows a pretty curvy pattern as well. It looks to be kind of like a parabola. Interesting. Okay, so let's to find which represents a geometric series, let's figure out first what is a geometric series. Okay, so let's draw this out. Let's get a thicker pencil. So a geometric series is a sequence of numbers, or a series of numbers, where each term is multiplied by something to find the next term. In this series. Okay, so let's say as an example of a geometric series, geometric series. We can have something like, we need something to start at. And let's say if we're multiplying by 2 every time, x2, so we get 2. Multiplied by 2 again, that's going to be 2 times 4, 2, that's 4. Multiplied by 2 again, that's going to be 4 times 2, that's 8. Multiplies by 2 again, that's 8 times 2, 16. And on and on and on. So to kind of easily tell if something is a geometric series or not, we can just divide the current term by the previous term, if applicable. Like, of course, we would not be able to do that for the first term. But we want to be able to see, like, our current term, if it has a previous term, if we divide them, we should always get the same number, no matter which term we're looking at. So 4 divided by 2, hey, that's 2, makes sense. 8 divided by 4, the previous term, that's 2, makes sense. 16 divided by 8, which is the previous term, that's 2, makes sense. We should look for that type of pattern among these graphs, and let's see if any one of these follow this pattern. And if it follows that pattern, we know it's a geometric sequence. Series and sequence, they're kind of similar. Yeah. So let's take a look at the first term. 1. The first term is when is 1. Its value is 1. Next value, 2, this value is 3. Let's do, okay, if we divide this from his previous term, 3 divided by 1, that's 3. You should take this and divide it by his previous term. 3 divided by, or 5 divided by 3. Oh, that's not the same answer that we got the first time. Let's say for up here, that's the 5th term. So that's 9 divided by 7. Hey, that's not 3. It seems like we cannot, there's no pattern or there's no number that you just multiply to the current term to get the next term. Because if that was the case, the number would be changing every time. And that is not what you would call a geometric series. Okay, so we can basically say A is no, not geometric. In fact, A is actually linear because you're always increasing by 2 between turns. So this is linear. Okay, cool. So let's look at B. Okay, let's look at the second term. It's multiplied. It's 2 times bigger than his previous term. Okay, 2 is 2 times bigger than 1. Makes sense. Term 3, 4. Term 3 has a value of 4. This is also 2 times bigger than his previous term, 2. And the fourth term, 8. Hey, that is also 2 times bigger than his previous term. This actually perfectly follows the pattern that we have here. I promise I didn't look at this before and use this as the example, but this really does follow our pattern. We can see that every term that we're looking at, when we divide the current term by the previous term, we always get 2. So we can write B is geometric. Every term is double the last, or double the previous. Okay, awesome. Let's take a look at C. You know, even though we found B and B is most likely going to be the match, let's make sure that we can disqualify the other 2 options from our question, from our options. Okay, so here we have option C. The first red flag is that, okay, our terms are not numbered in the greatest way. They're not 1 apart. They seem to be like, first it goes 1 and then it goes to 4 and then it goes to 9. At 4 it's 4, at 9 it's 6. It seems like the growth rate between the increase in y is pretty small compared to the increase in x. So its growth rate the growth is going to be smaller and smaller. Like the distance, the height change. Like initially we had a height change of 2 over a horizontal change of 4. Then on the next term we have a height change of positive 2 and a horizontal change of 5. This is going to be growing at a smaller rate, which is not what we observe with geometric series. Geometric series, you see the more terms you are deep into your sequence, the faster the growth rate between terms becomes. And here, we don't really see that pattern. And I think the main red flag is that these terms are not perfectly beside each other. So either we're skipping terms or something else is going on. Regardless, there are multiple things about C, like the growth rate decreases. And terms spaced out weird. It's probably the best way I can describe it. Regardless, we're disqualifying C from our possible options. And let's see if we can disqualify D. Well, its first term is 1. The second term is 4. So we divide the second term by its previous, we get 4. Okay. The third term, we get 9. 9 divided by its previous term 4. That's not 4 like we got for our previous. So this does not follow the geometric rule. This is actually a parabola, because it seems like the y value is just the x value squared. Like you see here, x value is 1, square that, becomes 1. X value is 2, square that, you get 4. For x value 3, you square that, you get 9. This is a parabola. Which is certainly not geometric. Because you're squaring your term number instead of multiplying something to your previous term. Remember, that's the golden rule for geometric sequences and series, is that every term divided by its previous term should give you the same number. You're always multiplying your current term by something, the same something every time to get your next term. In this example, we have times 2. This could easily be times 3, 4, 50, times 2 million. All be the same geometric series. Sounds good? Okay, so here in the answers, we got a choice B. And should we... I think the above solution is correct because... yeah, the above solution is correct. They disqualified everything that's not B. So, the above solution is correct. Awesome. So, we can move on to the next question on the menu. Okay. I really like this question. How do we find the equation of a tangent to a unit circle? I'm going to assume that we need to find the tangent line equation. Equation of tangent line to unit circle. First, let's figure out what is a unit circle. A unit circle, believe it or not, is a circle. Let's see if I can get a circular shape. Maybe move that to the center here. Yep, so a unit circle is a circle that has a unit or as radius of 1. So that's 1. This is -1. And that's also -1. Here we have our x direction and our y direction. So the equation of a circle, equation of a unit circle, is x squared plus y squared equals 1. That's the equation of this unit circle. So, for example, this point here, that is 1, 0. That would be like x equals 1, square that plus y equals 0, squared 0, so that's just 1 equals 1, makes sense. Perhaps we have a line like this, and over here, we'd have cos. Let's say that's 45 degrees. Here we'd have cos 45. Here we'd have sine 45. So our x value in that case, just to show how the a unit circle equation works out, example at point, let's say point P, and point P will have the values of cos 45, comma, sine 45. This would subbed into this equation over here. That would be cos 45, cos squared of 45 plus sine squared of 45 equals 1. And we know that cos squared plus sine squared of the same if the argument is the same is always equal to 1, so we know that this has to be right. So this is our equation for a circle, unit circle. This right here is what we set to the radius. Of course, we can make a bigger circle if we set this to a, like if this was 5, it would be a radius of 5. Okay, so that's a unit circle. Now, if we're trying to find a tangent to a unit circle, a tangent equation of the equation of a tangent line, we got to use some calculus. So a tangent line is essentially going to look like this. Let's see if I can get a line. Let's make this red, whole another color. So a tangent line is going to look something like that. Okay, a tangent line is going to look something like that, and we're going to try to find the equation of it. Now, this should instantly get some gears turning in your noggin about calculus, because if we take the derivative of stuff, we can find the slope of the tangent line. If we find the slope of the tangent line, we can find the equation of the tangent line, as long as we know where a point that it occurs. And if we know that it's going to be to a circle, of course we can figure that out. We can just use that point right there. Okay, so let's take this circle equation and let's find the derivative to this. Okay, find derivative. Let's say derivative with respect to x, because we're going to try to draw our lines in the same sense here. Find derivative with respect to x. And before we do that, we need to consider that y is a function of x. Meaning that when we take the derivative with respect to y, or derivative with respect to x of y, not only are we going to have just y by itself, we're also going to need to do this with the chain rule, because y is a function of x. So that means just taking the derivative by itself is not enough. We need to do the chain rule. So in this case, d by dx of just y by itself, that's going to be 1 multiplied by dy over dx, or it's just going to be y prime. Okay, but keep in mind we have to treat y as a function of x, and it will make sense in a minute. Okay, so let's rewrite this equation for the unit circle. X squared plus y squared equals 1. And let's take the derivative, or let's isolate y first. So we'll have y squared is equal to 1 minus x squared. And actually we can keep it like this. I think the calculus will be a little bit easier. So we're going to take the derivative with respect to x of both sides. D of dx of y squared equals d of dx of 1 minus x squared. Okay, so remember what I said earlier about y being a function of x? We're going to take the derivative normally, but we also have to multiply by its internal derivative. So this is going to be 2y multiplied by its internal derivative, so that's just going to be y prime, is equal to the derivative of 1, so that's just 0, minus 2x. Okay, so that's just negative 2x. Now let's divide both sides by 2y. Y prime is equal to negative 2x over 2y. The 2's cancel out on the top and bottom. They neutralize each other. So that is negative x over y is equal to y prime. Okay, so that's gonna be the slope to the tangent line of a unit circle. Okay, and we're gonna need to use that to help us find that's gonna help us find the equation to the tangent. So if we're trying to find the tangent, we found the slope. We're gonna need to sub in the point x, negative x times divided by y. That actually makes perfect sense. Like if it's at the exact 45, you would expect the slope to be negative 1. As we get closer to x, this should get more steep, meaning that x is getting bigger and y is getting smaller. So its magnitude is getting bigger, but it's getting more negative. So that makes sense. And the same thing, if we go more towards 0, it should look something like this. If I draw a line, the slope, like right now, is like this, but if we go more towards 0, it's gonna like flatten out like that. So x would be getting smaller and y would be getting bigger, so it would be getting smaller. So that makes sense. It's always good to think about the problems from multiple different directions, so we can cross-verify with different strategies, and if our cross-verifications lead to the same result, we know we are probably on the right track. Okay, so this is the slope, and to find equation to tangent line, we're gonna need to think about the equation of a line. So we know that a line equation is y equals mx plus b. And we're gonna typically want to solve for b. So let's isolate b by doing y minus mx is equal to b. And inside of m, we can sub in our derivative that we found previously right here. So that can be y minus x over y of x is equal to b. Or we can rewrite that as equal to a y plus x squared over y. This will be our b value. Okay. We should write this like y of a, x of a, to specify like this is a specific tangent line. Y of a, x of a, y of a, x of a, and these are this is going to be a particular point. Actually, I should not have compressed those two. I'm going to erase that. Or I guess the x's are going to be the same. Yeah, the x's are going to be the same. My bad. So I'm gonna erase this x. It's just like the y, the height of the height on the line particularly is not always gonna be the same as the or never mind. What am I doing? I'm tripping. Yeah, we do need to keep them separate because the x and the y on the line are not always gonna be the x and y of the circle. So this is gonna be x a. Okay, so this is our B equation. If we sub this back into here, it'll make a lot more sense. And this is y of a. So y of a is equal to x over y, negative x over y, times x of a. So those are points on line, on tangent line. And that is, those x and y's, let's say xc and yc, are points on circle. So we have that. That's our slope times our x of the line plus our b value. And our b value is this thing. Plus ya plus x over y xa. Now, a general equation like this is going to be a little bit problematic to be solving, unless you set you're typically going to want, if you are asked to ever find the equation of a tangent line on a unit circle, they will typically ask you at a specific point, and you will need to sub in that point to these processes, or to these equations to get it right. So there's no easy way to do like a general equation. Let's do a specific example of the slope of the tangent line, or equation of tangent line. Of tangent a line to circle at the point, we know one point that we certainly know that is on the thing, is on the circle, is cos 45 sine 45. Okay, so let's say we want to find the specific answer for this. So we can go to these equations, and we know that our x value is cos 45. We know our y value is sine 45. Okay, given that, we can make some subs into our equation right here to solve for b. I guess the xa and the subscript a and the other ones are going to be the same. So we know that we're looking for the base. And that's equal to y plus x squared over y, right? Yep. We're actually going to compress the xa and the regular x because we're going to take these points into consideration for calculating the point. So we know that y is equal to sine 45 plus cos 45, all that squared, over sine 45. And we know that our m is going to be negative x over y. And we know that that is going to be negative cos 45 over sine 45. Okay, busting out my fancy calculator. Gotta set this to degrees. If I can find the button that does that. Awesome, found it. So if we have sine 45 plus cos 45 times cos 45 divide sine 45, that is equal for the base to be positive 1.414. It makes sense because that is, it's going to be, if we scroll up to our unit circle here, it's going to be higher than the 1 if we're taking it here. So that makes sense. Not necessarily too much higher, but just a little bit higher. So that lines up with our calculation of 1.414. Awesome. So then we can find our slope, which is cos 45 divided by sine 45. I believe that's negative 1. I'll just verify. Yep, it is just negative 1. So our final equation for our slope is y equals mx plus b. So tangent line equation at the point cos 45 sine 45. And I explained previously why those were points. We know that that is going to be like an equal distance away from, it makes a 45-degree angle, and if we're going to calculate the x component, it's just going to be cos. If we calculate the y component, it's just going to be sine of the angle. That's how we got these points to begin with. So the tangent line equation for a line that is tangent to this point is going to be y equals negative 1 times x plus b, which is 1.414. So that'd be our final answer if we wanted to find the tangent line to the equation the equation of the tangent line to the tangent line that intersects with the unit circle at an angle of 45 degrees, or the point that is 45 degrees away from the center or the x-axis of the unit circle. Yeah, this one. Sounds Gucci? Sounds good. Okay. This answer is a little bit incomplete. Does not address finding the equation of a tangent line to a circle. Okay, gotta write that in as a question that I found to be incorrect. Cool. So let's move on to our next question on the menu. What is sine x divided by cos x? Let's say that's just our function here. Our function, let's call it f. F for function is sine of x over cos of x. Now, the question is pretty open-ended. What is this? Well, it is just a function. So if you wanted to, maybe if you wanted to do like f of, let's say, 30 degrees, you could just sub them in directly and deal with it that way. So sine 30 degrees divided by cos 30 degrees. That's going to be something I calculate real fast. This is just an example. Sine 30 divide cos 30. That's going to be 0.57735, on and on and on. But it really is that simple. You can treat this as a function, but let's say you're a little bit lazy and you don't want to like type this all into your calculator to calculate it. Oh my goodness, typing that many buttons, unacceptable. We can add a little bit more, or we can do something to this to make it simpler. Sine divided by cos x. So let's think back to our SOHCAHTOA triangles. Oh, nothing but good times here. SOHCAHTOA. So let's say that's our angle. This is our hypotenuse. Let's call that hype. I'm hyped up for it. Here we have our opposite. Not scared of the ops here. And here we have the adjacent. The amazing adjacent. That's the adjective I describe with adjacent. We know that sine of the angle is equal to opposite divided by hypotenuse. We know that cos of the angle is the adjacent divided by hypotenuse. Okay, so there's something else here. We know a tangent is opposite over adjacent. Up over adjacent. Let's actually send these equivalences into our original equation here. So originally we had sine of x. Of course, x and theta, you can use either one. Cos of x is equal to, well, sine on top is opposite over hypotenuse. On the lower end, we have adjacent over hypotenuse. We can rewrite this as op over hypotenuse multiplied by the bottom but inverted, so we have hypotenuse on top and adjacent. Oh, I see some mathematic magic. The hypotenuse on the top and the bottom of the fraction, they neutralize each other to 1. So sine of x over cos of x is actually equal to 1. I mean, not just 1. 1 times opposite over adjacent. And what does that equal to? Hey, that looks familiar. Tan. Tan of x, I guess in this case. So, anytime you see sine over cos, you know that, hey, I could do this manually like this, but why would I when I know that this is really just tan. Tangent. Okay, does that sound good? Does that sound beautiful? Look clear? Anytime sine over cosine, I kind of think of it like a trapezoid. So you know sine has like 4 letters. And cosine has 6 letters. You know, it makes like a little trapezoid. It's kind of like an umbrella, and you use the umbrella to maybe avoid a tan, but you don't want to avoid the tan always. The tan is good. We say tan Q. Tan Q. Yeah. Okay, so that would be the solution to this question. And it seems that they have a similar description on how they came to the same conclusion. So sine x divide cos x, that's the same as tan. think of the trapezoid and an umbrella for tanning. That's my way of thinking about it. So the above solution is correct. Cool. Sounds amazing. Awesome. Okay. So the next question that we have on the menu is how to graph a natural logarithm of x. Or ln. Some people call it ln, like a lawn chair, lawn. Okay, let's say that's our main function of x. F of x is equal to ln of x. A good strategy that you can use for graphing is just to find a couple points of interest. So when x is equal to 0, we get error. And actually for logarithms, x must be greater than 0. It cannot be equal to 0. If it's equal to 0, it's not good. Very bad, very bad. So we're only going to draw on the right-hand side of the graph. So if this is our Cartesian grid here, all this end, illegal for log and ln. Okay, so that's nice. We only need to draw like basically half a graph. So, okay, if x is equal to 0, we know that this is no answer. Which means we have an asymptote, or a vertical asymptote, at x equals 0. Okay, let's say x equals 0.1. Y is going to be a natural logarithm of 0.1. In our calculators, that is going to be negative 2.303. Okay, let's say x is equal to 0.5. Like we're going to do it all the way up to 1 and then we'll speed up. But essentially we're trying to find some points of interest so we can start drawing the points and then we just connect the dots. It's a fairly simple strategy. So let's say at 0.5 we have natural logarithm of 0.5. Y is equal to natural logarithm 0.5. That is equal to negative 0.6931. Hope it don't tell on me. Awesome. So the next one that we have, let's say x is equal to 1. Well, what's the natural logarithm of 1? That's something that you kind of, it's a nice shortcut in the mind that you can remember. The logarithm or natural logarithm of anything or of base anything of 1, that's going to be 0. Oops. It's equal to 0. Let's say x is equal to the base. And the base in this case is e, which in this case is equal to 2.718 on and on and on. Y is equal to natural logarithm of the e, and that is also equal to 1. So typically when you're drawing logarithm graphs, there are two nice points that you can always rely on being there. X equals 1, y equals 0, and x equals base, y equals 1. Okay, and I think that really should give us quite a lot of the stuff that we need to just start drawing the graph. Okay, so I will draw just the right side of it because we know the left side, when x is negative, that's kind of irrelevant. let's get rid of this line that I put here. Technology sometimes does not cooperate, but that's okay. We can still make it work. So I'll draw that a little higher because we do have negative values. There we got x, here we got y. 1, 2, -1, -2, on and on. Here we have 1, 2, 3, 4. Okay, so let's we basically just want to fill in our points of interest. So we know at x equals 0.1, y equals -2.303. I think we can draw that just around there. That looks reasonable. Okay, now for x equals 0.5, y equals -0.6931. So just about halfway through here, and a little slightly over half closer to 1. And we know that 1, 0 is always going to be a nice point. And now we gotta look at our base. Our base is 2.718. That's the Euler's number. So that's going to have a height of 1 just around here. Okay, so with our 4 points of interest, we can pretty much just draw a line that connects them. Let's do that in blue. And we know that our line is going to pretty much follow this path on and on. And we could calculate more points of interest, but what's just important is that you have like these 2 major points of interest, like the x equals 1, y equals 0, and x equals base. So that's E. X equals the base, and y equals 1. Those are the main points of interest when you're drawing a logarithmic graph. Sounds good. Awesome. So this is our graph, and just points of interest. Gotta know them. Keep them ready. Okay, cool. And seems like they got the graph from there. It looks good. Okay, let's verify that and clear this up. Okay, so the next question on our menu is the derivative of 10x, or 10 to the power of x. So if our function is f of x, and that's 10 to the power of x, we need to find f prime of x, or d over dx of 10x. Okay, now this is a exponential function. So this is the general rule. General rule for exponential derivatives. D over dx of some base to the power of x is equal to the natural logarithm of the base multiplied by the base to the power of the same thing. And this is why when base equals e, or Euler's number, we get something like this. So d over dx of e to the x equal to logarithm of e, and that neutralizes to 1, e to the x. That's why we get the derivative of e to the x, simply just itself. Okay, but here we have the base is not e. Our base is not e because it's not e, and it's 10. So let's take this general rule and apply it to the base equals 10. So f prime of x equals d over dx of 10 to the power of x, which is equal to the natural logarithm of the base, ln of 10, multiplied by itself to the power. If there was some function in the top of the power, we would need to do the chain rule, but that is not the case. So this could be our final answer. Okay. Natural logarithm of 10, that's about, I'll get an approximated value for that. It's about 2.3. $2.3023. But you would typically want to leave it as a logarithm, just to give you an idea, like of what it's gonna look like. So what that value might be in this case is 2.3023, but higher bases are gonna have higher values for this. And yeah, that's how you find the derivative for an exponential. Not just for base 10, but for any exponential, use this general rule and then apply it to your situation. In this situation, we had 10 to the power of x. That's all. Cool. So we can verify that the above solution is correct. Okay, so the next question on the menu, what is the square root of 18? Square root of 18. Now, you might be thinking, I'll just stick that into my calculator. I'm going to get a nice number for that, of course, right? Square root of 18. Let's do that. It's 4.242640. Oh, wait a minute. How many decimals are you supposed to write? You don't know how many decimals you're supposed to write. Like, should we write maybe 3 decimal points? Should we write 300 decimal points? We don't really know. And what if all of them are important? Like, what if we need 1,000 decimal points of precision and we only included 3? That's going to be an issue. So we want to be able to write this in a simpler form, so that we can write it so that we can more easily understand what its value is. Okay? So this is a strategy. You want to first look at under the root. Look at value. Under root. And what we want to do to it is we want to see if we can factor things out. Okay, and let's try to do it as many times as possible. Get as many terms under the root as possible. So basically looking for smallest factors. Or if you find a factor that also has factors, keep on factoring it out. So let's think about 18. We know that 18 is 3 times 6, right? 3 times 6, whoops, not 3. 3 times 6 is equal to 18. So we have 3 times 6 under the root. Hey, 6 is 2 times 3, right? So we can do root under the root 3 times 2 times 3. Okay, now when we get all of the terms under the root to be prime numbers, essentially, we can combine them. Hey, we got 2 3's. How about we write them as 3 squared? 3 squared times 2 And here's the magic part. Anytime you have something squared under the square root, you can bring it outside and drop the square. And remove power 2. So this will be equal to square root of 18 is equal to 3 times the square root of 2. So we brought the 3 out. The 3 was brought out like this, and it lost its power. And everything left in the root is a prime number, so we can leave it that way. And yeah, overall, this is a better solution to the square root of 18 because we know that like the square root of 2, we know that's about 1.4 or so. Triple that, it's a lot easier to deal with that as opposed to, this big root. Yeah, it's more easy to understand it. Sounds good? Awesome. So, yeah, the above solution is accurate. The above solution is correct. Okay, now I need to check something real fast before I hop onto this question. I need to check that no one is trying to stream right now. Awesome, so I can go for another little bit of time. Okay, awesome. So we got our next question on the menu. We can keep the stream going and keep the math magic happening. Our next question, also a little bit mathemagic. So we got Jill, and she got a fish that is 8 times heavier than a parakeet. That's a heavy fish. I think a parakeet is a bird, right? So that's a heavy fish. Together, the parakeet and the fish are 63 ounces together. That's a couple pounds. I think there's 16 pounds or 16 ounces in a pound. So it's a couple pounds. How much does the fish weigh? That's a heavy fish if it's 8 times heavier than a parakeet. Let's ignore like all the biology stuff and let's just focus on the math. So with this sentence, we can extract some equations from here. So let's set up some variables and give them and show what they represent. So if we have f, let's call that f, and that will be fish weight. And let's say p, this will be parakeet weight. This might be a shark or a very small parakeet. Okay, so we know that the fish is 8 times heavier than the parakeet. So, fish weight is equal to, fish weighs 8 times more than a parakeet. So 8 parakeets are going to be 1 fish in weight. We're not going to think about the biology. This is a big fish. Like, this is a shark. Okay, so we got the fish is 8 times heavier than the parakeet. The parakeet's weight times 8, that's the fish weight. Okay, together the pets are 63 ounces. So 63 ounces is equal to the weight of the fish plus the weight of the parakeet. Okay, so we can actually isolate the weight of parakeet. of P, and we know that that is P is 1/8 the weight of a fish. We can sub that into here. And we know that 63 is the weight of the fish plus the weight of a parakeet, which is 1/8 of a fish. We can actually add these together. So that's going to be 9/8 fish is equal to 63 ounces. So we can multiply both sides by 8/9 times 63 is equal to 8/9 times 9/8 of the fish. Those neutralize and those neutralize. So we know that the weight of the fish, 8. So this is going to be 8 times 63 divide 9. So we got 56 ounces of fish. The fish is 56 ounces. How many pounds is that? 16 pounds in 1 ounce. That's 3.5 pounds of fish. That's a heavy fish. Maybe not a shark, maybe a baby shark. But so the fish weighs 56 ounces, and the parakeet is going to be much lighter at 7 ounces. So the parakeet is like 1/2 pound, and the fish is 3.5 pounds. Heavy fish, but yeah, it all works out. In the end, the math is actually very simple. Of course, there's all these distractions of like the fish and the context of it, but that's close to real life, because you're never just going to be given just an equation. You'll have to derive an equation given a real life situation, even if these real life situations are confusing and involve extremely heavy fish that are 3.5 pounds. But it's all good. The above solution is good. Okay, so the next thing that is on our menu is graph the 6 terms of a finite series where A1 is equal to 5, A1 is equal to 5, and R is equal to 1.25. Okay, so the keywords that you're going to look for is like your A and the R. Those typically mean geometric series. And R values suggest geometric series. Now, what is a geometric series? Well, a geometric series is essentially that the term value of geometric series is A initial multiplied by R, which is what you're going to multiply to the power of n minus 1. Okay, so in the first term, R is basically what you multiply current term multiplies by this to get next term. So the first term we know is going to be 5. So a1 is equal to 5. a2, the second term, let's actually not write first terms, let's just write our terms. The terms that we're trying to find. So the first one, they give it to us, that's 5, and that's shown by the subscript here. The second one is going to be 5 multiplied by 1.25. So that is 5 times 1.25. I think that's 6. I'm going to double check. 1.25 times 5. 6.25. Uh-oh. 6.25. That's why you should not always trust yourself. Always trust the calculator. Okay, now if we multiply that by 1.5 again, 1.25 times 1.25, 7.8125. Okay, multiply by 1.25 again. We get a 4 times 1.25. That's equal to 9.765625. Going to multiply by 1.25 to get the next term. Times 1.25. We get a5. That's equal to 12.20703125. And we only need to find 6. That's what the question asks us to do. So multiply 1.25 for the last time. A6, that's equal to our previous number multiplied by 1.25. We get like 15.25878906, on and on and on. As our decimals get longer and longer, the less relevant they are. Typically only need like 3 or 4 at the beginning, and the rest should be good. But these are our first 6 terms. And they appear... Oh, 625. I guess there's only two more digits. My calculator just was not showing them. But yep, as you can see, it is a geometric series because the keyword that let us know about that is r equals 1.25. We know that every term is going to be 1.25 times bigger than its previous term. And you multiply your current term by 1.25 to get the next. Okay, so I think we can say that this question is done good. The above solution is correct. Super. Okay. So, the next question that we have, what is a radical? Well, they're pretty rad. A radical typically looks like this. So you're going to have something, possibly some numbers, possibly some variables. Numbers and variables. Anything that's underneath a root, and you might have a number here, n. Radicals, they're kind of tough to think about. It might be better to just recognize that, let's say you have like n to here, and we have x. It's good to know that you can essentially rewrite them as a power. So x to the power of 1 over n. And typically these will be easier to deal with in math. It'll be easier to type these into your calculator. Like, you don't need to like make sure what's under the root and what's not under the root. If you do it like this, everything under the root you just put in brackets, and you raise the everything between the brackets up to the power of 1 over whatever values here. If you have just a square root like that, like x, that is equal to x to the power of 1 over 2. Square rooting is so common for radicals that if there's nothing specified, assume 2. Okay, so another example of how we can convert these into something a little bit more easy to deal with is maybe we have like 13. This would just be x to the power of 1 over 13. And let's say you get like a very strange situation where you get something like this, like the root or the radical, such that you have a fraction up here. Don't fall for that trap. Take the reciprocal of whatever is here, and that's going to be the power. So that's going to be x squared. Okay, I seriously doubt that you'll see any fractions in your radicals, but it is possible. So your calculators often will typically have a square root button. Maybe they'll have a cube root button if you're lucky. But otherwise, if you see a radical like this and it's giving you trouble, convert it to a fraction. And I mean, convert it to a power with the power being the inverse of whatever is on the radical. Because this way you just throw that into your calculator and generate the result. Sounds good. Okay, the above solution, something up with that. The above solution has fourth root of 25, and then shows fourth root of 24. So radicals, keep in mind, they're just to the power of typically a fraction. Sometimes it might even go the other way. Like if you see to the power of 1/2, oftentimes they will just convert it to a square root. But yeah, anytime you see something that's like more than 2 or 3, typically convert it to a fraction on an exponent, and it'll be a lot easier to deal with. Sounds good? Awesome. Okay, so we can move on to the next question that we got. Okay, so the arc CD, I assume that it is, I'm going to redraw this with like the annotations on it so that we know what we are talking about. Seems pretty good to pretty close to circular. Let's say that's the center. So arc CD, let's say that is C and that is D, and we're looking for this angle. It tells us that the arc CD, like to go from C all the way to D, is 2/3 of the circumference. So that is 2/3 of circumference. Meaning that they left over 1/3 of the circumference to be, I guess, not included in this measurement. If we're trying to find this angle in radians, we know that the angle is also going to be 2/3 of a complete cycle. So the angle will also 2/3 of complete angle. And our complete angle in radians is 2 pi. So 2 pi is the angle that you do if you go like starting at C, loop-de-loop all the way around back to C. That is the complete angle of 2 pi. So the angle here for 2/3 of the way through is just going to be 2/3 of the way through this entire angle here. So angle, let's give that a name, CD. Let's call this A. So angle A is equal to 2/3 of 2 pi. That's equal to 4 pi's divided by 3. And that is angle A. So just as a recap, we got to know that our arc length is 2/3 of the whole circle, and we know that that's only possible if you're also doing 2/3 of the full angle of the whole circle. The full circle is 2 pi radians for the central angle, and 2/3 of that, 4 pi divided by 3, as our math shows, and that would be our final answer. Sounds good? Awesome. So yeah, they did it by converting it to degrees first, but you could do the whole thing in radians. But I guess you could convert it to degrees. The above solution is correct. Okay, our next problem on the menu is how do we find the area or the volume of a triangular pyramid? So let's draw a triangular pyramid, or I guess we should specify a triangular base pyramid, because all pyramids have triangles, but if they specify a triangular, that means they have a base. That's also a triangle. So if I were to try to draw one, it would maybe look a little something like this. Maybe it'd be better if I draw this as like a dotted line to show that this is like behind the current plane. And an unfolded look at a triangular pyramid would look a little something like this. Kind of reminds me of Zelda. But yeah, you could see like if you fold up all of those, like it's kind of like a flower with its petals spread out, and you see like if all the petals folded in, it would make a nice pyramid shape with a triangular base. Okay, so to find the volume of a pyramid is really just simple. We find the area of base times the height divide that all by 3, and that is volume of pyramid. really is that simple. We can run through an example. I'll draw out all the dimensions on an unfolded view, so we can all be clear on what it all means. Kind of see how that could fold up into a pyramid. Let's go and take some geometric thinking to see how that works out, but I promise it does. This will make a pyramid when you fold it up properly, I think. Yeah. Okay, so let's call this our base. All these triangles are the same. So let's say we have, they're all equilateral triangles. Yeah, this definitely works. And let's say they have, the equilateral triangle has a side length of 3 centimeters. So find volume. Volume of pyramid once folded 3D. Okay, so if that's 3 centimeters, we know that's 1.5 centimeters. And an equilateral triangle is really just two twin 90-degree triangles. We know that that's 1.5 centimeters. We know that that's 3 centimeters. We need to find this, our horizontal side, our vertical side, rather. So we know that this, with Pythagoras' theorem, this is going to be the square root of 3 squared minus 1.5 squared. And that's with Pythagoras' theorem. So we know that that is going to have a height of so square root of 3 squared minus 1.5 squared. So that is equal to 2.5981. Just about centimeters. Okay, so let's say that we have a we want to have, let's calculate our base area. Our base area is really just like this half triangle multiplied by 2. So it's just going to be 2 times 1.5 centimeters multiplied by its height, which is, I'll write the full version, 3 squared centimeters minus 1.5 squared centimeters. So that multiplied by 2 times 1.5. That's going to give us the area of the base, which is equal to 7.79423 centimeters squared. Okay, so that's the base. Now we got to find the height. Now, since we know that all of these equilateral triangles are the same, we can pretty much conclude that our side profile of the pyramid is going to look like this too. Meaning that its height is going to be 2.5981. Since they're all equilateral triangles, like all of those triangles are going to make a 60-degree angle with like the ground, and the top is also going to be a 60-degree angle if we look at the pyramid from the side. So we know that the height has to be the same. So we know that the final volume is going to be the base area multiply that by the height, divide that all by 3, and this is what we'll get. So let's write in our full equation for the base area. It's actually just oops. So like that. Guess we'll have to rewrite it because technology is hard. 2 times 1.5 centimeters. The units are important because let's say we give it in centimeters and later on we forget and we write like kilograms. That's going to be an issue. 3 centimeters squared minus 1.5 centimeters squared. Like the whole thing squared, not just the centimeters. Multiply by the height. And this is the height, so we can really just square this. Divide by 3. So let's calculate that. Volume is equal to calculating this real quick times 2 times 6.75 centimeter cubed. That would be how we calculate the volume of a pyramid. You got to find the area of the base and you got to find the height. Once you got to multiply those two together, divide by 3, and that's the volume of the pyramid. Sounds good? I think so. Okay, so the solution here is really just saying like okay, yeah, it's just square units. I feel like we're talking about square square base pyramids, but the equation is the same for a square base pyramid. It's also going to be area of base times the height divided by 3. But a square base is going to be a little bit easier to find the base because you don't need to chop it down into like right angle triangles. Okay, cool. So let's verify the solution. The above solution is correct. Okay, so our next question on the menu is find the integral of cos x. The integral of cos x with respect to x, of course. Let's think about this. An integral is really just like find something that's derivative is what we're looking for the integral of. So we're basically saying what's the integral of something is cos of x. Find that something. Well, we know that like one of the fundamental trigonometry things that we need to know for calculus is that the derivative, the d by dx of sine x, is equal to positive cos x. So that's what we get right there, and it really is that simple. But we have to remember something very important, is that when we take the derivative of a expression that has something added to it, or like two terms that are added together, we take their derivatives separately, and we know that constant numbers have a derivative of 0. So d over dx of constant equals 0. So if we think about it, the d over dx of sine x plus constant is equal to cos x plus 0, which is a little bit more accurate because this is just equal to cos x. These two also have like just sine x and sine x plus some constant. These have the same derivative of just cos x. Well, this is really just the same thing except the constant is 0. So we want to go with this definition to include the constant. So we know that like the actual integral of this, the actual result is going to be sine x plus constant of integration. Never forget it. If you ever forget the constant of integration, a problem that can possibly occur is that, let's say you need to do an integral of something multiple times. You know the integral of a constant is going to be the constant times x, or whatever you're taking your derivative or your integral with respect to. So if you forget a constant and you're doing multiple integrations, that will eventually lead to an incorrect result, which is not at all cool. You don't want to have wrong answers. So always keep in mind constant of integration when you do this. Like, it's simple enough just to find the integral, but you could crash the boat if you just forget the constant. So always remember that. And the integral of cos x is simply sine x, because we know the derivative of sine x is cos x. But don't forget the constant. Constantly be thinking about the constant. Sounds good? Awesome. Okay, so the above solution is correct. Okay, and I guess that concludes our last questions that I selected for today. Awesome. Just gotta do something super fast. Okay, well, those are all the questions for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you'd like to submit your own questions, also visit the links in the description. And remember to leave a like and a comment if you enjoyed the video. Share it with your friends if you think this could help them. And remember to spread love, because the world needs more love. This has been Millan with OneClass, and I hope to see you soon. Goodbye. Have a good evening. Or morning, depending on when you're watching this.